Namaskar students. Today in this video we shall discuss a variation of the first principle of mathematical induction, and then we shall move on to solve a problem using that variation. So let us start today's video. See, by the general first principle of mathematical induction, we can say that if Pn be a statement involving some natural number n with the following two conditions, such that P1 is true. P1 is true means in place of n we are putting 1 and checking whether the statement Pn is true or not. So if P1 is true and the second one P of k plus 1 is true whenever Pk is true. What is k? K is any natural number which is greater than equal to 1. In some books you can find k is greater than 1 also, because for 1 it is already proven to be true. Then by these two conditions you can conclude that Pn is true for all natural numbers n greater than equal to 1, or rather to say for all natural numbers n only, because natural number starts with 1. So this is the general first principle of mathematical inductions detail. Now sometimes in variation it might happen that P1 is not true. Does it always mean that the first principle of mathematical induction fails? Here comes the twist. It might be that P1 is not true, P2 is not true, P3 is not true, but P4 is true, P5 is true, P6 is true. I mean that for us here in this example, P1 is not true, P2 is not true, P3 is not true, but from P4 onwards, you are finding that the statement is true for all natural numbers n. So this is the variation. It says that P1 might not be true, P2 might not be true, but there might exist some natural number for which P is true. Let that natural number be, suppose, n0. For some natural number, suppose Pn0 is true. And we might see that after that natural number onwards, all are true. So the variation is that Pn0 is true, Pk plus 1 is true whenever Pk is true for some k which is greater than equal to, or you might say greater than n0. Then you can conclude that Pn is true for all natural numbers greater than equal to n0. So this is the variation. I'll just repeat once again. See, the previous general principle of mathematical, first principle of mathematical induction, it says that you have to test whether P1 is true or not. After you are testing P1 is true, then you consider that let the statement be true for some natural number k which is greater than 1. And then you are proving that, okay, if Pk is true, then Pk plus 1 is also true. And then you are concluding by the first principle of mathematical induction that Pn is true for all natural numbers n greater than equal to 1. I mean for all natural numbers n. The variation states that for the first natural number 1, the statement might not be true. Even for the second natural number also, the statement might not be true. So after 1, except 1, there might exist another natural number after 1. It can be 2 also, it can be 3 also, it can be 4 also, for which the statement is true. And after that natural number onwards, for all other natural numbers, the statement is true. So the variation or the generalization, you might say, for the first principle of mathematical induction, it says that let us suppose that for some natural number n0, Pn0 is true, and consider Pk to be true for some natural number k which is greater than equal to n0, then prove that Pk plus 1 is true. After you prove that, okay, if Pk is true, then Pk plus 1 is also true, then you can conclude that Pn is true for all natural numbers n which are greater than equal to that first natural number n0. So this was the variation of the first principle of mathematical induction. Now let us move on to a problem which depicts or shows this variation. This is the problem for today's discussion. It says that you have to prove that n factorial is greater than 2 to the power n for all n greater than equal to not 1 but 4. Here the problem demands that you have to prove that this statement is greater than equal to is true for n greater than equal to 4, not for all natural numbers n. See why? See, for the first natural number, if I say n equal to 1, what is 1 factorial? In place of n put 1 factorial is 1, and what is 2 to the power n? 2 to the power 1, that is 2, which is not greater than. So this inequality does not hold. See, for n equal to 2, 2 factorial means 2, and 2 to the power 2 means 4. So 2 is also not greater than 4. For n equal to 3, 3 factorial means 3 into 2 into 1, that is 6. And what is 2 to the power 3? That is 8. Again, which is not greater than. So for n equal to 1, 2 and 3, this inequality does not hold true. What about n equal to 4? See, for n equal to 4, 4 factorial means 24. 4 into 3 into 2 into 1, that is 24. And what is 2 to the power 4? Means 2 into 2 into 2 into 2. So 16. Now see, 24 is greater than 16. What about n equal to 5? So 24 means 5 factorial, that is 24 into 5. 5 4s are 20. 120. And what is 2 to the power 5? 32, which is greater than. And you can test for n equal to 6, 7, 8, so on. You will see after the number n equal to 3, that means from 4 onwards, this statement is holding true. So this is an appropriate example of our today's discussion, that there might be a statement which is not true for all natural numbers n, but it might be true after a certain natural number, starting from a natural number. This is the variation of the first principle of mathematical induction. Let us now formally try to solve this problem using that variation of the first principle of mathematical induction. Here let Pn be the statement that n factorial greater than 2 to the power n. So here we have to start with not 1 but 4. Let n equal to 4. So we have already shown that for n equal to 4, 4 factorial is greater than 2 to the power 4. 2 to the power 4. Therefore, we can say P4 is true. Coming to the second part, let k be some natural number which is greater than equal to 4, such that Pk is true. Now Pk is true means k factorial greater than 2 to the power k. Now we shall prove that Pk plus 1 is also true. Now to prove Pk plus 1 is also true, we have to show that k plus 1 factorial is greater than 2 to the power k plus 1. That we have to show. See, it's very simple to show that k plus 1 factorial is greater than 2 to the power k plus 1, considering k factorial is greater than 2 to the power k. Why? See, already we have considered k factorial greater than 2 to the power k. Now what will happen? if we multiply both sides with k plus 1. Now consider this as equation star. Now equation star implies k plus 1 into k factorial greater than k plus 1 into 2 to the power k. So you are multiplying both sides with k plus 1. Or now see, it's so simple. K plus 1 into k factorial means k plus 1 factorial. So it's k plus 1 factorial, which is greater than k plus 1 into 2 to the power k. Now see, what is k? K is greater than equal to 4. K is greater than equal to 4. So if k is greater than equal to 4, k plus 1 is a greater number than k, which is also greater than 4. It's very simple. If a certain natural number is greater than 4, then k plus 1 means what? The natural number which is greater than k after k. So k plus 1 is also greater than 4. Now 4 is greater than 2. So using this transitive logic, we can say k plus 1 is greater than 2. So if I write 2 in place of k plus 1, if I write 2 in place of k plus 1, here the inequality will be greater than, because k plus 1 is greater than 2 and over here you have 2 to the power k. So k plus 1 into 2 to the power k is greater than 2 into 2 to the power k, because k plus 1 is greater than 2. Now considering this, you have or k plus 1 factorial is greater than 2 into 2 to the power k. What is 2 into 2 to the power k? That is 2 to the power k plus 1. See, if I say k plus 1 factorial is greater than 2 to the power k plus 1, it means that the statement is true for n equal to k plus 1, because in place of n, if you put k plus 1, you get this statement. So from this you can say that, which implies p of k plus 1 is also true. Thus what we have shown? We have shown that P4 is true. Then we have considered Pk to be true. After that we have proved that Pk plus 1 is also true. Thus, by the variation of the first principle of mathematical induction, we can say that the given statement Pn is true for all natural numbers n greater than equal to 4. My dear students, if you have understood whatever is discussed in today's video, do like this video, share this video with your friends, follow my page and don't forget to subscribe to my channel. Till then, goodbye.